Assalamu alaikum and hello everyone. Welcome to Mathematics with Shahab Yaqub. We are studying AS level math, paper 1 that is, and we are focusing on this particular topic of functions. Now, when we talk about functions, one of the things that usually comes in functions is about whether a certain line is a function, a certain graph is that of a function or not. So we apply the vertical line test. Let's write this thing as VLT. Now, VLT differentiates whether a certain graph is the graph of a function or a certain graph is that simply a relation between two variables. Now, that brings us to the idea what exactly is a function. Let me make you go through it so that you understand. Let me write fx is equals to 2x plus 1. If I plug in a value of 3, that is 2 into 3 plus 1, that gives me 7. That means a value of x is equals to 3 is giving me a y value, a function value of 7. That means 7 can only be obtained from 3 and there is no other place. There is no other way of obtaining it. So there is a unique value of function and it is obtained by one particular value of x. That is one kind of a function. If I have something like fx is equals to x squared, if I plug in -2, I get +4. If I plug in +2, I get +4. That means this particular unique value, yes, it's one single unique value, but there were two options of obtaining it. A -2 is giving me +4. A +2 is also giving me +4. That means +4 can be obtained from -2 as well as +2. This is also a function. But for example, if I talk about fx equals to square root of x, and there is a plus minus sign on the outside, if I plug in x is equals to 9, therefore f of 9, it's square root of 9 with a plus minus sign. So I'll be getting a +3 and a -3. That means this plus minus 3 is obtained from two different, two values of x were obtained from one single value. So one single value of x is giving me two different values of 3, two different values of the function. That means even though it's written as a function, it's not a function, it's simply a relation between two variables. So that is the theoretical definition of a function. Now, when we talk about the vertical line test, so vertical line test is a graphical way of checking whether a certain function, a certain graph is that of a function or not. So now I'm leaving this pages blank, and let me show you the vertical line test VLT application. So let's get started with this. Let me make different kind of functions. For example, if I draw a graph of a straight line, and let's say, let me draw the graph of a quadratic. Let me draw the graph of a cubic. I'll label each one of them separately. Let me draw a reciprocal function. Let me draw an exponential function. Let me draw a trigonometric function. So now these are different examples that I've drawn. And let me label it. So when I label it, this is like y is equals to 2x plus 1. So let me write over here, y is equals to 2x plus 1. This is like y is equals to x squared minus 2x. This is y is equals to x cubed. This is y is equals to 1 over x. This is y is equals to 2 raised to power of x. This is y is equals to sine x from negative 180 degrees to positive 180 degrees. All good? Now I want to apply the vertical line test. So let me draw a vertical line anywhere on the graph. So let me first draw a vertical line, and I'm applying the vertical line test. So let me draw a vertical line over here like this. Let me draw a vertical line over here, a vertical line over here, another vertical line over here, a vertical line over here, and a vertical line over here. And I need to draw two more graphs. So let me draw a circle over here, and let me just shift the circle a bit. And let me just erase this thing. And let me draw a graph, something like this. Okay. So now this is the equation of a circle, which we will soon study. So let's say x squared plus y squared is equals to 4, and this is y is equals to plus minus square root of x. And let me draw a vertical line also over here. So that's a vertical line like this. That is a vertical line like this. Now the thing is, let me draw the vertical line properly. Okay. Now the thing is, if the vertical line cuts at one point, if it cuts at one point, this is the graph of a function. And if it cuts at more than one point, then it's not a function, it's simply a relation between two variables. So this is, yes, a linear function. This is also a function, a quadratic function. This is also a function, a cubic function. This is also a function, a reciprocal function. This one is an exponential function, a power function. This one is a trigonometric function. The same holds true for a cosine x or tangent x. This one is not a function. This one is not a function. It's simply a relation between two variables. And now we can focus on the diagram also. One single value of x is giving me two values of y. One single value of x is giving me two values of y over here. That means when the domain is 1 and you are getting two values in the range, so this is just a relation between two variables. So now we have studied this thing in class also. And over here, just acknowledge it on the WhatsApp that we have done VLT, and this is all good, all clear. So AS Math 1, AS Math 2, I'll just wait for your responses and then we will continue. Now we would also do something else that is called a horizontal line test. So now let's discuss about HLT, horizontal line test. So this is HLT. Now, what is a horizontal line test? Now, a function can be of two types. A function can be one-to-one function. A function can be many-to-one function. When we use the terminology one-to-one, it means one value of x is giving me one value of y. When we talk about many-to-one, many values of x giving you one value of y. So it is necessary there should be only one value in the range, because that is what makes it a function. Now, the very basic example of one-to-one function is a linear function. it can also be an exponential function. And some common examples of many-to-one function will be a quadratic function, a cubic function, a trigonometric function, and so on. Now, the rule is, what we will do is that we will draw a horizontal line on the graph. It's a horizontal line test. If it cuts at one point, it is one-to-one. If it cuts at more than 1 point, it's not one-to-one, it's many-to-one. So let me draw it over here. So now, if it cuts at 1 point, so let me use a green marker. If it cuts at 1 point, it will be a one-to-one function. And if it cuts at more than 1 point, so it's not one-to-one, it's a many-to-one. So it's a function, that's for sure. But we are differentiating between one-to-one versus many-to-one. So now what we can do is that, first of all, let me draw and let me choose this color. Okay, something reddish color. And then I'm choosing one-to-one and many-to-one. Okay. So let me draw this thing in purple color. Actually, a black color would be fine. So now, first of all, a straight line, then a quadratic, then a cubic. Actually, let me draw a cubic like this. And let me flip it. Okay. Okay. Let me draw a power function. Let me draw a trigonometric function. And what else? Linear, exponential, quadratic, cubic, trig. I think that's about it. And a reciprocal, yes, a reciprocal square. Let me draw this. Okay. So now over here, all these are functions. Let me write it. This is, let's say, y is equals to 3x plus 5. This is y is equals to x plus 1, x minus 2. This is y is equals to a cubic function, x minus 2, x plus 2, x minus 1, x minus 3. This is y is equals to 3 power x. This is y is equals to cosine of x. It's starting from negative 90 degrees and it's going till 270 degrees. This is y is equals to a 3 over x squared. Now, all these are functions. I'll apply the horizontal line test. So which color am I choosing? I'm choosing a purple color, or let's choose a green color. So let me apply the horizontal line test. So HLT, and let me draw this thing. So over here, if I draw a horizontal line, over here, I'm drawing a horizontal line. Let me make it thicker. Over here, I'm drawing a horizontal line. Over here, another one. Over here, another one. Over here, another one. So now a linear function is one-to-one. So red one, this is 1, 2, 1. Blue one, this is many, 2, 1. So first of all, let me mark it. And it's over here. It's cutting at 1 point. It's cutting at 2 points. It's cutting at 3 points. It's cutting at 1 point. It's cutting at 2 point. It's cutting at 2 point. So the 1.1 is a one-to-one function. So therefore, this is a one-to-one function. This is a one-to-one function, and that's it. This is many-to-one. This is many-to-one. This is many-to-one. This is many-to-one. So you can also see over here, One value of x is giving me one value of y. Two different values of x are giving me the same value of y. Three different values of x are giving me same value of y. Two different values of x are giving me same value of y. Two different values of x are giving me same value of y. So that is the differentiation between a one-to-one and many-to-one. So now HLT sketches, this is all done, and just acknowledge it on the WhatsApp that this is all good, all clear. So now let me convert a many-to-one function into a one-to-one function. So I'm converting a many-to-one function. Many, for a second, many-to-one function. I'm converting it into a one-to-one function. Now, the best example that we can work with is quadratic. So a quadratic, by default, it's a many-to-one function. That is the default value. But I'll convert a quadratic into one-to-one. Now, how will I be able to do it? So let me just check if there is the grid thing over here. Okay, this thing is good. And let me copy this. Okay. We all know the original quadratic. Now, the original quadratic is this thing that's right over here. So let me draw it in purple color. That's like this. And let me draw the grid around it. So therefore, that's the vertical axis. That is the horizontal axis. And let me shift the graph properly. So this is the original one. That is fx is equals to x squared. That is the original quadratic, and that is the turning point. That is y-axis, that is x-axis. Now, let me change the domain. If I change the domain, so first of all, let me draw on this side. And let me draw a little bit like this. Let me draw on this side. Let me draw like this. And let me draw and one other one. Now I have drawn 6 snapshots of this. And I'll apply the horizontal line test. So let me apply HLT, horizontal line test. So let me draw this thing, a horizontal line, another one. And I'll just be writing down the domains over here. So first of all, the domain for this one is x is greater than or equal to 0. The domain for this one is x is less than or equal to 0. The domain for this one is x lying between, let's say, 1 and 3. This value is 1. This value is 3. There is a 0 over here. There is a 0 over here. Over here are the domain -1, -2. Domain x lies between -1 lesser than or equal to -1, and this is -2. Over here, let's say this is -2. This is +4. Domain x lies between -2 and +4. Over here, domain, x lies between -5 and +3. So it's not drawn to scale. This is -5, this is +3. Now, what do you observe? We observe that it's cutting at one point. So let me just highlight this. This is cutting at one point, cutting at one point, cutting at one point, cutting at one point, cutting at 2 points, cutting at 2 points. So this one is a one-to-one function. So let me choose a color. Green is good. So this one is one-to-one. This is one-to-one. This is one-to-one. This is one-to-one. This is one-to-one. And the other one, the cross, that is many to one. So this is many to one. This is many to one. Now, what is the observation over here? The observation over here is, excuse me, if you start from the turning point and you go right, if you start from the turning point and you go left, if you ignore the turning point, go further ahead, go further back, it is one-to-one. But as soon as you cross the turning point and then you rise up, the horizontal line will cut you into two. As soon as you reach the turning point and then rise up, the horizontal line will cut the graph into two. So basically, it's the turning point that makes all the difference. So turning point, it makes all the difference. It can convert a many to one function into a one-to-one function. As long as turning point does not lie in the middle, it is a one-to-one function. You can start with the turning point, go right. You can start with the turning point, go left. You can ignore the turning point, keep on going right. Ignore the turning point, keep on going left. But as soon as you cross the turning point and then you rise up or fall down, it will slash. The horizontal line test will be failed. Is this all good, all clear? So now we talked about quadratics and we converted many to one, to one, to one. And the decision maker, the game changer. So the decision maker is the turning point, also known as vertex, also known as stationary point. And that is the terminology that we will use in differentiation. So I have written it in the WhatsApp so that you know exactly the different things that we are going through. Okay, all good, all clear. Now, what are we reaching at? Now we are interested in a one-to-one function, and there are some reasons for it. So now my focus is one-to-one function. And once I have explained this, then I'll share all the images for you to first write it down comfortably, because the past paper questions that I'll do, that will require all this knowledge. So I'm interested in one-to-one function. The very first reason is only one-to-one function has an inverse. Because I'm interested in one-to-one function, I'm interested in inverse function, and we are just working towards that. Only one-to-one function has an inverse. I can also say inverse only exists for a one-to-one function. The second one, that is the graph of y is equals to fx and y is equals to f inverse x, they are reflection of each other in the line y is equals to x. Therefore, a point such as AB will become BA. Therefore, the domain of original becomes range of inverse and vice versa. And also, it is not necessary that the graph of fx and f inverse cut each other, but if they cut, if the graph of y is equals to fx and y is equals to f inverse x cuts each other, or cuts means intersect each other, they will intersect at the line y is equals to x. And there are two further points which I'm not writing at the moment. So now this is the knowledge that is needed. So let me pause the recording. Let me share the things with you so that you can really understand what we are going to do next. So let me pause it. So now let's apply all this knowledge that is over here related to one-to-one function, inverse function. Only one-to-one function has an inverse. The graph of y is equals to fx and y is equals to f inverse is a reflection of each other in the line y is equals to x. Therefore, a point AB becomes BA. Therefore, domain of original becomes range of inverse and vice versa. It's not necessary that the graph of fx and f inverse cut each other, but if they do, they will cut each other. They will intersect each other at the line y is equals to x. And then there are 2 points which are related with expression for f inverse. And these two are specifically for quadratic. So that is specifically for quadratic, not just for any inverse. So this is quadratic over here. Okay, so let me get started. Now I'm working from this topic number 2. That is about functions, and these are the type 1 question that we are working on. Now let's look at question number 1, and let's do it in step by step. Now the first thing is that express this thing in this form. The second thing is for the curve, state the least value and the corresponding value. The third one, find the set of values for which y is greater than or equal to 14. Now, these 3 parts, they are related with quadratics. So the first 3 parts, they are completely related with quadratics, and the rest of the parts, they are related with function. So first, focus on quadratics. Now, the blue part, that is right over here, the blue one. So that is part number 1. That is about completing square method. We have to show the whole process. Now it says express this thing in this form. So 2x squared plus 8x minus 10. What is the first step? Make sure the coefficient of x squared is 1. So 2 is common. X squared plus 4x minus 5. Now let the 2 remain on the outside. X squared minus 4x. And this is, let me just double check, that is plus, this is plus, my bad. And this is first add, then subtract square of half the coefficient of x. So this is the coefficient of x, half of that is 2, and you have to add and subtract square of half the coefficient of x. We will rewrite these 3 terms as a perfect square. So this is x plus 2 whole square. The rest of the thing is written as it is. There is 2 on the outside. This is -4, -5. So let's open it up. So this is 2x plus 2 whole square minus 18. That is in the completed square form. Now be very, very vigilant. They are not asking us the value of a, b, and c. So they're not asking us the value of a, b, and c. They're asking us to write in this form. Now, always remember that our gold standard for the completing square method is ax minus h whole square plus k. That is the gold standard by which we will judge everything for stationary points and the shape of the graph and all these things. So now over here, this is part 1. Let me just write over here underneath it. I'll write this is a, this is x minus h whole square plus k, because it's a question of quadratics. It's a question of some other things over here. So over here, when I do comparing the coefficient, so this is extra. So a is 2, h is -2, and k is -18. If a is positive, that means that's the shape of the graph, and -2, -18, that's the coordinate of the turning point. So just hold for a second. Let me do some adjustment. So now that's the shape of the graph. That is the turning point. Now, first of all, over here, the first part was done and dusted. So that is up till here. Now, why am I doing this thing? Because it is related with the second part, which says for the curve, state the least value of y and the corresponding value of x. It is about the turning point. And for turning point, you need this. So basically, the working for part 2 starts from here. So over here, what I'm doing, that is the working for part 2. So the x coordinate of turning point is -18, -2, and the y coordinate of turning point is -18. The y coordinate is the least value, because if you draw the graph, that's what it shows. And this is the corresponding value of x. So now let me just show you a simple grid, a simple graph over here. Okay, I think that's the one. No, not this one. Using this one. So if I draw this thing, -2, -18, let me draw the graph like this. And over here, this is -2, this is -18. This is the lowest value, and that's how the graph is drawn. So that's the first thing. And the second thing. Now the third thing, that is this thing, which is about what? The third thing is about a quadratic inequality. Now in quadratic, the way in which the equation is written makes a lot of difference. The first one is completing square. The second one is using completing square to get the stationary points, the turning point. For quadratic inequality, now we need the general form. And use, based upon the general form, we will solve the quadratic inequality by drawing a sketch. And the sketch will be based on the factorized form. So everything that you have studied will be used over here. Find the set of values, the range of values of x for which y is greater than or equal to 14. This is y. This is y over here. 2x squared plus 8x minus 10. 2x squared plus 8x minus 10 is greater than or equal to 14. This is part 3. Divide by 2, x squared plus 4x minus 5 is greater than or equal to 7. X squared minus 4x minus 12 is greater than or equal to 0. Middle term factorization, x squared minus 6x plus 2x minus 12 is greater than or equal to 0. X bracket x minus 6 plus 2 bracket x minus 6 is greater than or equal to 0. X minus 6, x plus 2 is greater than or equal to 0. And now what do? We draw a small sketch. So over here, a sketch will be drawn. And we have to mark the roots. So the roots are what? -6 is giving me +6. -6 is done. +2 is giving me -2. We are interested in greater than or equal to 0. That's the region above x-axis. So it's 2 separate regions, 2 separate answers. Go extreme right, go extreme left. Therefore, x is greater than or equal to 6 and x is lesser than or equal to -2. Because when you go to the right, the y values increases. When you go to the left, the y values increases. So that's how you draw a sketch based upon a factorized form, and then you will look and write down the answers. Look and write down the answers. Keep that in mind, because quadratic inequality, drawing a sketch is a must. So drawing a sketch is a must. So this is all about the previous quadratic that we have studied. So just have a good look. The first part, completing square. The second part, based upon the completing square, we get the turning point. The least value is -18. The corresponding value of x is -2. And the third part is quadratic inequality. So now have a good look at it. I'll just minimize it. And in the WhatsApp, this is question 1. The quadratic parts, chord parts, it's all done, all clear. So just acknowledge it. AS Math 1, and then AS Math 2. Okay, now let's move to the next parts. So now it says something about a function. So part 4 is about functions. And part 5 is also about function. And I'll also add a part 6 over here. And I'll write it a little bit soon. But let me just add a page over here. And let me tell you one thing. Let me draw a grid. So over here, that's a grid. And let me show you something. Now let's say I have an equation. Fx is equals to x minus 1 whole square plus 4. This is A, x minus h whole square plus k. A is positive, h is 1, k is 4. That's the coordinate of the turning point, 1, 4. Now, let me draw 2 images of the same graph, actually 4 images. So first of all, let me draw it this way, like this. For a second. Like this. Let me just copy it. And like this. Now let's say this is the turning point. That is 1, 4. So over here it's 1. Over here it's 4. If the domain is x is greater than or equal to 1, my question is it a 1-to-1? Is it a 1-to-1? The answer is yes. Because we are going to the right of turning point. So yes, it's a 1-to-1. Now, what if I go to the right of 2? And I'm just focusing on this thing. So if I just focus on this part, is it still 1-to-1? Yes, it will pass the horizontal line test. So once it has passed the horizontal line test, it is 1-to-1. So now x greater than or equal to 2. Let's say if the domain, this thing is 2 and this thing is 5. And let me just simplify it a bit over here. So is it still 1-to-1? Yes, it's still 1-to-1. Now, if they ask me x is greater than or equal to q, the function for the domain, x is greater than or equal to q, the function is 1-to-1. Write down the least value of q. So now, if I draw this number line over here, so over here, this is the turning point 1, this is 2, this is 3, this is 4, all the way till infinity, it's 1-to-1. So out of all these values, they could also be decimal value. This one, the x coordinate of turning point will be the least value. Also remember, Whenever they would ask us for greater than or equal, they would be asking us the least value, and that least value will be x coordinate of turning point. And this is in the context of quadratic. Does this thing make sense? The least value, the greater inequality, and let me write the greater inequality. And what are we getting at? That is the x coordinate of turning point. So just acknowledge if this is all good, all clear. And some people are a little bit slow in acknowledging. So this is AS2. Okay, so AS2 is done, AS1 is done. So now least value and all this thing. I think I wrote it twice in the same group. That's AS2. So let me write. Okay, least value. AS2, AS1. Okay, AS1 people can also write it. So now this is all good, all clear. So now let me look at the same graph and let me draw it the other way. So let me choose a blue marker and let me just draw it like this. And let me draw it like this. So now over here, it's the same graph. And now the domain is x is lesser than or equal to 1. And now the domain is x is lesser than or equal to 0. And let me just stick this thing over here. Okay. So now it's the same function, fx, that is x minus 1 whole square plus 4. So when I plug in 1, this value is 4. When I plug in 0, this value is 5. And in both cases, it is 1 to 1 because it passes the horizontal line test. It passes the horizontal line test. Therefore, if I write it like this, 0, actually negative, positive 1. So first of all, positive 1, then 0, then negative 1, then negative 2, and so on. Now the question they will ask is that for x lesser than or equal to p, the function is 1 to 1. Write down the greatest value of p. So now look at the inequality. The inequality is lesser than or equal, they will ask for the greatest value. The inequality is greater than or equal, they will ask for the least value. Now, out of all these, the x coordinate of turning point is the greatest value because all the other values are lesser than this. So therefore, the value of p is 1, that is the x coordinate of turning point. Over here, the value of q is 1, that is the x coordinate of turning point. So whether they ask for the least value, whether they ask for the greatest value, the answer is always x coordinate of turning point. Whether they ask for least, they ask for greatest, and it is about 1 to 1 function. Maybe they can say that they can ask about inverse exist. Inverse exists for a 1 to 1 function, and only 1 to 1 function has an inverse. So that is the logic that's applied over here. Now let's focus on part 4. Now the same thing that you were dealing with upstairs, this thing over here, which they have written as y, for which you solved a quadratic inequality, now they are calling it a function. So what difference will it make? It's the same thing. So for part 4 and for part 5, and for part 6, they will all be connected. I'll just be writing part 6 over here very soon. So now this is like this. For all these things, this is related with functions. So it's about functions. It's about domain and range. It's about inverse. It's about least and greatest values, and so on. And this is again related to of greatest and least value are related to domain. Now, first of all, your fx is x minus actually 2 bracket x minus 2 whole square. I think it's plus 2, x plus 2 whole square minus 18. Let me just go ahead and double check this original one. This is 2 bracket x plus 2 whole square minus 18. All good. A is positive, that is the shape, and negative 2, negative 18, that's the coordinate of the turning point, which is in fact a minimum point. So now they're asking find the least value for which f is 1 to 1. So simply write it. The least value for the domain x is greater than or equal to k. For x is greater than or equal to k, the function is 1 to 1. The function is 1 to 1. And they're asking us the least value. Why are they asking us the least value? Because the inequality is greater than or equal. They will ask for the least value. That is the x coordinate of turning point, which comes out to be negative 2. No need to draw anything. If they would have written this question like this, for x is lesser than or equal to m, the function is 1 to 1. This part I'm writing it myself. Find the greatest value of this thing, of this constant m. So m would be x coordinate of turning point, that is negative 2. So this is part 4, that is done and dusted. Now part 5 and part 6, let me now write part 6, that is on the same grid, draw the graph of y is equals to fx and y is equals to f inverse x. And let me write part 7 also. Write down the domain and range of y is equals to f inverse x or f inverse x. So there is part 6, there is part 7 also. So there are 4 parts to it. So let me just adjust it. All got all clear. Hold for a second. So there is part 4, part 5, part 6, part 7. So this is part 4 that's done over here. Now these 3 parts are related. What are they? Express f inverse x in terms of x in this case, that I'll do at the very last. On the same grid, draw the graph of y is equals to fx, y is equals to f inverse x for this domain. The value of k is what? That is negative 2. And write down the domain and range on the same grid. Now, this is the main thing. So let me just put a grid over here. Okay. And let me check the recording and everything. Is it all good? Recording is on, alhamdulillah. So now that's all good. So now the very first thing that I need to do is that this is the x-axis, this is the y-axis, and let me label the coordinate of the turning point, negative 2, negative 18. So let me just push this down a bit. Okay. And let me mark over here, negative 2. And let me mark over here, negative 18 over here. And let me also mark one other thing. So I just need to readjust the thing. Something like this. And this is negative 18, 1, 2, 3, 4, 5. So 2, 3, 4, 5. This is negative 18 and this is negative 2. So let me make 2 columns. Let me write fx. Let me write f inverse x. And this is the most crucial thing that you will study in functions. One of the most crucial things. There is a point, negative 2, negative 18. It gets flipped. It gets negative 18, negative 2. That is the first thing. So negative 2, negative 18 is marked in red. That is right over here. And negative, this is not 12, this is 2. Hold for a second. So this is the black one. That is negative 2, negative 18, negative 2. That is marked in blue. All good. The next thing, right over here, domain right over here range, right over here domain, right over here range. And let me just push this thing a little bit to the side. So a little bit over here. Domain of F, domain of range of F, domain of F inverse, range of F inverse. The domain is always written in terms of X. Whether it's for the original or for the range. The range for F is written as Fx. The range for F inverse, it's written as F inverse X. And then an inequality. So I'm just getting all the template ready. Okay. So hold for a second. Okay. So now it's all good. Now, first of all, let's draw the red graph. The red graph is going like this, and it goes like this. Hold for a second. That's how the red graph is drawn. Okay. Let me also draw a line in green color. That is y is equals to x. So this is the line in green color. That is y equals to x. And let me make it dotted. So dotted, dotted. Okay, all good, all clear. So let me write over here. This is y is equals to x, the red one. That is the turning point. That is y is equals to fx, the red one. And by looking at the graph, tell me the range. The lowest value is negative 18. When we go to the right, because the domain is x is what? X is greater than or equal to k. X is greater than or equal to negative 2. Fx is greater than or equal to negative 18. Does it make sense? So greater than or equal to negative 18 is going like this. So domain, range, function, fx. So I have written domain, range, the function fx. This is as1, this is as2. Now this is all good, all clear. I have drawn the line y is equals to x. Now the thing, let me go up. And we wrote over here. Only one-to-one function has an inverse. That is to the right of turning point or to the left of turning point. Doesn't make a difference whether the turning point is included or not included. Y is equals to fx, y is equals to f inverse x. The reflection, this thing is done. This thing is in the process. If the graph of fx and f inverse cut each other, it will cut at the line y is equals to x. So let's go back over here. So now the coordinates are flipped, negative 18, negative 12. Let me choose a blue marker and let me draw it like this so that it intersects over here as accurately as possible. I think that's very nice. So now black marker, y is equals to f inverse x. That is the blue color thing. Y is equals to fx. That's the original thing. Where are they meeting? They are meeting at the line y is equals to x. That's how the graph is drawn. So now the inverse thing is also done. So the inverse graph is also done. Okay, I'm just going step by step so that we all are together on one page. So what have I done? I'm working with part 4 and part 5 and part 6 and part 7. There is also the 7 over here. So now it's all connected. It's all one thing. What I did is that, first of all, that is something that they asked, which is x coordinate of turning point, 2 basic. Now I'm drawing the graph. The original graph, its reflection, the coordinates flipped, negative 2, negative 18 became negative 18 and negative 2. And function f inverse, domain of original will become range of inverse and vice versa. So now this thing will become this. This thing will become this. The original domain, of the original function or the inverse, it's always written in terms of x. Just copy this thing down from here. So just copy this thing. Greater than or equal to minus 18 will be written over here. So this is greater than or equal to minus 18. Similarly, this thing will be transferred over here, and you can also see it on the screen. This is greater than or equal to minus 2. Now, in the inverse, when we are going to the right of negative 18, the y values of the inverse are increasing from minus 2 upwards. So this is negative 2, the y values are increasing. You go right, the y values are increasing. All good, all clear? On the same grid, draw the graph of fx and f inverse x, write down the domain and range. That's also done. Express f inverse x in this case. Now over here, what I need to do is this thing. The thing is, when we talk about quadratics, it is necessary that the original quadratic function should be in the completed square form. Otherwise, we cannot make x the subject, because we are interested in finding expression for f inverse x. And the last thing is, the original is quadratic, has a square in it. The inverse is radical function, has a square root in it. Now, this rule that I'm going to tell you, I'll also prove it. If we go to the right of turning point, the square root will have a positive sign. If we go to the left of turning point, the square root will have a negative sign. And just take it for granted for right now, till the time that I prove it. So now over here, what I'm doing is that the expression, it's a very, very long question because I've added 2 parts to it also. So now part number 7, I can work it out over here. Let me just remove this thing. So now this thing is basically part 5. So part 5, that is expression for f inverse. Now we know this thing that let y is equals to fx. Therefore, f inverse y equals to x. Basically, what they are saying, that's the input. This is the output. In the inverse function, you plug in the output, you recover back the input. This is something that you've studied in O-level maths, but you are understanding it now. So this is something related to inverse. So now what we will do is that we will write fx is equals to 2 bracket x plus 2 whole square minus 18. Fx is replaced with y. Y is equals to 2 bracket x plus 2 whole square minus 18. Y plus 18 divided by 2 is x plus 2 whole square. And square root y plus 18 divided by 2 is x, and I'll give it a positive sign. Why? Because the domain of original function was x is greater than or equal to negative 2. That is the original quadratic function. The domain was to the right. So we give it a positive sign. What is x equals to? F inverse y. X equals to f inverse y. In other words, f inverse x is equals to, and one more thing, I forgot the plus 2. So there is a plus 2, take it to the other side. So that becomes negative 2. So x plus 2, hold for a second. And let me add something, a step, so that you don't get confused. And let me just remove over here. So this x plus 2 is this thing. Let me make x the subject, that is negative 2 plus square root y plus 18 divided by 2. Now, what is x equals to? X equals to f inverse y. So in other words, change the variable. F inverse x is equals to minus 2 plus square root x plus 18 divided by 2. And there is a plus sign over here. Now, let's double check whether we are on the right track or not. So let me choose a value. Let's say I choose a value which is 0. That means in the inverse function, if I plug in 0, I should get some positive value over here. Okay. So now let me plug in f inverse of 0. So that is minus 2 plus square root 0 plus 18 divided by 2. That is minus 2 plus 18 over 2. that is minus 2 plus root 9. That is minus 2 plus 3, which comes out to be positive 1, which makes sense. That means if I plug in 0, it should give me 1. In other words, if I would have plugged in 1, it would give me 0 in the original function. But right now, I'm just focusing on this. So if I would have taken the negative sign over here, what would happen? Instead of positive, it would give me negative, which is against what you have seen on the grid. So 0 is not giving me negative, 0 is giving me positive. That means this decision is perfectly good, perfectly all right. So remember the thing that right of turning point, we are talking about domain. Domain, right of turning point, and we are talking about the original quadratic thing. The going to the right of whatever value, the square root will have a positive sign. If the domain is left of turning point, x is lesser than or equal to something, then the square root will have a negative sign. So positive, that is to the right of the original function. Negative, left of the original function. Doesn't make a difference whether the graph is has a minimum point, has a maximum point. No issue with that. The issue is just with right or left of turning point. So that is functions, the quadratic function, the inverse thing, that is explained in great detail over here. And I'll be sending you some questions for you to try it out for tomorrow's class, to do go through them. And I'll also share these images so that you can copy them down. Till the very next class, take care.